Matt. Hello, everyone. Thank you for coming. Abby leads UCL Women in Physics at UCL, and I look after the Thomas Young Centre and the MMM Hub at UCL. We are really excited to welcome you to the first in our careers events. So thank you for joining. We're excited to introduce our representatives from the UK Atomic Energy Authority, Helen, Tom, Julita, Debbie, Katie, Michelle and Sam, to talk about the sorts of careers available at UKAEA. Thank you, and I'll hand over to Sam to introduce his colleagues and outline the event.
Thank you very much, Karen. I'll share my screen if that's okay.
Yeah.
And okay, can you all see that? Yeah, can everyone see my screen?
Yes, you're sharing.
Perfect. Thank you. Okay, thank you very much, Karen and Abby, for that introduction. So yes, we are a team from the United Kingdom Atomic Energy Authority, UKAEA, and today we're presenting engineering analysis and high performance computing you can get across is that in distinct roles at UKAEA is that people specialize in these areas, but they certainly do in many companies and especially at UKAEA. So we want to give a flavor of our work in these areas, talk about life at UKAEA more generally, and encourage anyone who's interested in a career with us to apply. At the end, there'll be some time for open questions, and we'd be very grateful if you could fill in a survey to help us improve the presentation. Okay, so who are we? This is our mission. It is to lead the delivery of sustainable fusion benefit. Essentially, the end goal is fusion power stations providing affordable and sustainable electricity to national grids. Okay, so what is fusion then? Fusion is the process that powers the stars, including our very own sun. In space, the gravity is sufficient to hold everything together, but on Earth we need confinement, and we use a magnetic field to do this. The reaction itself is deuterium and tritium atoms colliding at very high energy, and they fuse together to form a helium atom, and in the process release a neutron and energy. And it's this reaction that has the potential to provide abundant energy to supply the growing global energy demand. We have two sites at UKAEA. We have our Culham Science Centre in Oxfordshire, which is home to the UK's two largest fusion experiments, the Joint European Torus, which is owned by Eurofusion and operated by us. And we have MAST Upgrade as well, which is our own experiment, and MAST stands for Mega Amp Spherical Tokamak. Very recently, our Advanced Manufacturing Park in Rotherham in South Yorkshire has also opened. The government in 2019 invested 220 STEP, which stands for Spherical Tokamak for Energy Production. This is a prototype reactor, so a power plant planned to be built in the UK from 2040. And all of us speaking today have been involved in this project in some way. Okay, so then what are engineering analysis and HPC? They are distinct but related disciplines. They rely on the underlying systems of equations that describe the phenomena that we're interested in. In engineering analysis, we're generally using commercial software to solve these equations. In HPC, it's usually open source or the user's own software to solve them. In engineering analysis, we're interested in single physics and increasingly multi-physics, and our problems are generally limited to about 32 cores. In HPC, it's usually multi-physics and also multi-scale, highly parallelized, often with well over 1,000 cores. We both submit our jobs to the same cluster, and we both have the end goal of improving the designs of our components. Now, as part of the UKAEA digital strategy, actually the line between these two disciplines is being blurred a bit with a move towards a common open source platform used by both engineering analysts and HPC specialists. Okay, who are we then? We are a group of engineers and physicists dedicated to solving problems in fusion using computational methods. And today we have Helen, Julita, Sam, Debbie, Katie, Michelle, and Sam, myself. And now each of us are going to talk about our own individual areas of work. Starting with Helen. Helen isn't actually here today, so I'm going to talk through her slides, but Helen is an HPC software specialist in the advanced computing group. A brief background: she did natural science at Cambridge, followed by a PhD in theoretical particle physics at Durham. Then she did a postdoc in particle physics at Monash in Australia, and she joined UKAEA last summer. And her work is building towards a digital tokamak, essentially a simulation platform that combines all the physics in the tokamak in one place. And part of the goal is to simulate emergent phenomena. So these are phenomena that come about from the interactions of different physics. You can't predict these phenomena from looking at the individual physics themselves. You have to model all the coupling, all the interaction in order to see what can happen. But ultimately, the goal of this tokamak simulator is to improve the design of future power plants. But it is an immense computational challenge. It's been estimated that up to 1 quintillion, that's 10 to the power of the 18 floating point operations per second, will be required to simulate all the physics involved. And actually, there's only one machine in the world at the moment, this Fugaku in Japan, that's capable of this level of performance at 1.4 exaflops. It's called the exascale 1 quintillion. I think on a typical book might have 10 to the 5 words in it. A very large library has up to 1 million books, so that's 10 to the 11. And if you had 10 million of those large libraries, you reach the exascale at 10 to the power of 18. So just mind-boggling number of calculations per second required. And the range of scales is phenomenal as well. So to incorporate all the physics in the tokamak, we go from the kind of femto scale, which is on the far left here, some kind of atomic interaction, and then going up the scales, we might be interested in radiation damage on materials, then further up material grain structures, leading it into kind of engineering, deformation, for example. Going up the scale again, we're interested in fluid dynamics, and finally, on the meter scale, full-scale tokamak components. And all of these different physical systems are governed by different systems of equations, and each of those systems of equations requires different numerical methods. So on the lower end of the scale, we need Monte Carlo simulations, and on the higher end, it's more finite element and finite volume. And so we need to couple all these different numerical methods together, and we need to do it on complex geometries as well. And so the way this is done is discretizing, breaking up those complex geometries into discrete elements, and then the calculations are performed on those elements and then assembled together to form a global picture of what's going on. And Helen has been working on an open source application called Aurora. And at the moment, it couples a neutron transport code with heat conduction and thermal expansion. And even with these three domains of physics, we have a complex feedback loop being set up. So for example, the neutron transport leads to a heat flux and a change in temperature and density, and ultimately that affects your cross-section for your neutron calculations, and so that in turn affects your heat flux, heat conduction, and thermal expansion. So even with these three levels of physics going on, we have a complex dynamic loop that you cannot predict its behavior just from looking at the individual parts. But Helen's ongoing work is to add fluid dynamics to this picture and the physics study, and then in the future, electromagnetism and other domains of physics. So this gives you just some kind of idea of the complexity involved with the tokamak simulator. Okay, so now we will. Julita, are you able to, can you hear?
Yes, I'm here. Do you see me?
Yes, yeah, I can hear you, yeah.
Okay. Will you help me, please, with moving the slides, right?
Yes, of course. Yeah.
Thank you. My name is Julita. I was born in Lima, Peru. I'm showing in the map where Peru is in Latin America. I'm currently Linux ambassador of the projects of Fedora and Genome. I did a master in the University of Edinburgh in regards of high performance computing, HPC. Now, well, I became in last year an HPC software specialist at UKAEA. I'm working in the STEP project, which is working to accomplish the tokamak simulations by the 2040 in the Advanced Computing Group with Helen. Go forward, please. If we want to make it possible, we need to break down the pieces of the tokamak. One of them that I'm showing you right now is the diverter. In this case, we are dealing basically with multi-physics phenomenon and heating loads. So the final goal I am saying again is to make this possible, this hybrid simulation. We have many systems, so we need to couple those transient state system mostly. You can see how is this project about in YouTube. Next one, please. Sam. Sam, please, the next one. It doesn't go. Yeah, that's fine. I mean, during this year, I learned some. I have to learn some, reinforce some background related to how to make these simulations possible. What I'm encouraging ladies is to take into account linear algebra basis. To do the discretization, you can make it with many models or methods, I'm sorry, but we are using the finite element to set up the equations as well. We are using different orders of Lagrange. If we have to arrange these equations into a matrix, we can put it into a space, like the Krylov subspace, preconditioning. If we have to solve those problems, like derived from the finite element methods. In my case, my study is about applying preconditioners, with they are going to help some iterative methods in 3D, mostly in 3D phenomena like the neighbors, incomprehensible neighbor stock, for example. Additionally, you have to have some computational skills. We are using MOOS. It's a framework that is already developed to simulate multiphysics. And if you are very interested in be part of this organization, I suggest you also to take a look of the programming part. Most of the HPC programs are developed in using C, C++, Fortran. You need to have knowledge of some algorithms to treat the trees. In regards to parallelization performance, the benchmarking I'm doing right now is using MPI and OpenMP. Next one, please. Oh, well, in combination, you have to take care about the physics, right? Multiphysics. These are some simulations that has been done using MOOS. And as you can see here, you have the deuterium concentration in the ether diverter, pneumonic blocks, and you are the image displays the different cycles on the movements. In the other hand, you have tungsten foam, so you can see the temperature distribution throughout these elements. and you can simulate complex fusion components that are going to be part of the tokamak. So my job is to discover what preconditioners might help to accelerate and have an efficient use of the resources in the cluster. I'm using the cluster of Cambridge right now. So that's all for my part, and I encourage you, lady, to be part of this challenge as well. Everyone can do it. Thank you.
Thanks, Elita. Tom, unfortunately, can't be with us today either, but he is an engineering analyst in the product engineering design group, and he has come from the automotive industry. Interesting collaboration with a physics group to develop a beam particle tracking tool that he wrote in Python. And what this has done is it's put particle tracking physics in the hands of engineers, which has been really powerful for us as a design group. This is a beam of deuterium ions, and we use beams to heat the plasma up to the required temperatures for fusion to take place. But the beam consists of ions of different charges and masses, and they deflect in different ways in magnetic fields, and we need to be able to predict the trajectories of these particles so that we can put protective tiles in place and stop those particles melting components that they may do otherwise. And this is a target that the beam hits once it's passed through the plasma. So this has been a really interesting tool that Tom has worked. As I said, it's put this new capability in our hands. Tom has also been working with our robotic maintenance testing facility that we have at our Culham site. This is a large robotic arm that would be used to perform remote maintenance inside a tokamak. And this is Tom's rigid body dynamics model. And Tom has been developing this model that can be used for both prediction and potentially even control of a robotic arm like this. He's been able to correlate the behavior of his model against measured data from the arm in a test facility. Okay, Sam.
Hello. Yeah, so my name's Sam Merriman. I'm an engineering analyst here at UKAEA. I studied at Strathclyde in Glasgow, and during that time I was on Erasmus in Malta. I did a group bachelor project on sort of small scale fatigue design. My bachelor project was on trajectory design of long range hypersonic vehicles. So completely unrelated to nuclear fusion. Next slide, please, Sam. So my current role at UKAEA, or the majority of my time, is spent as the design lead for outboard blankets on STEP. So this great little picture that we've got on the right shows a rough mock-up of a particular STEP design. And the blanket envelope sits just adjacent to the plasma. So the plasma is where we produce the energy. Being so close to the plasma, there's a couple of key roles, one of which is to capture the energy, convert it into something useful. The second of which is to take the neutrons from the plasma and actually produce the fuel for that plasma, sort of in a loop. And finally, the other main function, there are a lot more, but the other main one is to shield some of the components behind them. So as an engineering analyst, what I tend to do is to try and kind of use engineering analysis methodology to feed into design process and to inform design decisions where possible. So right now, because of an early stage of the project, what that is it's kind of low fidelity coupled multidisciplinary calculations. And really the aim is to allow, as I said, to allow us to kind of make more informed design decisions, more informed optioneering for a particular project. That then will allow us to hopefully come up with a design that can meet the requirements as we go through that design process. So in doing that, I support a team of engineers in Python development, some meta model work, parametric geometry. So that picture on the bottom right there is just a parametric geometry from published papers that we can then alter, like in Python, to generate new geometry and operate on that. And finally, thermal fluids analysis. Next slide, please, Sam. Next slide, please, Sam. Can you hear me? Thank you. So in some other work during my time at UKAEA, I've worked on the majority of the tokamaks at UKAEA, that's JET, MAST, and STEP. I've worked a little bit on ITER as well, and the EU demo program. So this is just some kind of more traditional FE, but again, using a coupled sort of workflow. So we're looking at custom physics codes, applying to thermal FEA, applying to structural FEA, and then producing a lifetime prediction. So you can see from the video that Sam just set off, we're predicting the sort of temperatures in this case in an area where we really don't know very much about because of we can't put any monitoring equipment there. So this system operates on JET right now, and the purpose of these kind of calculations is to predict how long we can operate and to what powers we can operate this particular system at. And I would like to mention at this point, FEA is a great tool, and it's really transferable across industries. So my background after I graduated was oil and gas. And I worked there for 4 years, and then I came to UKAEA, and I've been here for 5 years in November. But FE is really a kind of very transferable skill that you can apply to whether it's Tom coming from automotive industry, and I think Sam came from power as well. So it's really quite good in that way for you, from a career point of view. Next slide, please, Sam. So additionally to the sort of technical side of things, I spend 25% of my time working on JET as a neutral beam shift lead. So that's responsible for part of the experiment that we do at UKAEA. So that's interfacing with a lot of different people and making sure that the pulses in the actual experiments are set up, which is really quite a nice way of bringing you back to reality. When you spend a lot of your time working in the sort of pre-conceptual design space, understanding exactly what we need to do these experiments on JET is really an exciting time. And especially with the upcoming campaign on JET for the deuterium tritium, and also the really exciting work that's going on in MAST with the new upgrade. Yeah, it's a really interesting time to get an operation. Additionally, I sort of attended some conferences and did sort of outreach and MAST tour guides, etc. So yeah, it's quite a broad range of things you can get into at UKAEA. And I think that's me handing over to Debbie.
Sorry, I was muted. So yeah, thanks, sir. I'm Debbie. I was born in India, and I have been a bit all over the place, as you can see. I did my master's with nothing related to fusion at the moment. In fact, I didn't even know what fusion was, at the University of Delaware in the US, which is on the East Coast. But then I thought it wasn't cold enough, so moved all the way to Alaska in February to do a PhD. The application was fusion, but it could have been anything else because it was turbulence, which you find pretty much everywhere in nature. So, so it was a computational physics application to a turbulence case, which happened to be fusion. Then I was a postdoc in France at the ITER organization, which is where currently the biggest tokamak in the world is being built. So JET is currently the biggest tokamak in operation, and ITER is under construction. So ITER is going to be much bigger than JET though. So yeah, I was a postdoc there, and then I moved to the UK as an exascale algorithm specialist, and I've been here ever since. Next slide, please, Sam. Right. So just like the speakers before me, I have a whole variety of interests, and I mean, there is quite a variety in the things I do on my day-to-day job. But research-wise or work-wise, you can have all my interests under one umbrella, which would be algorithms. So algorithms are methods that are used to simulate, and those of I mean, with the kind of audience we have, you probably know what a simulation is, but it's basically we are an experimental facility, so we have real machines doing real experiments. But having said that, you need to calculate and you need to analyze the data, the results, etc. And for that, you need computer simulations. You do those computations on the computer. And how do you do that? So these involve lots of equations. How do you solve the equations? That's where algorithms come into play. So you have different methods basically to solve these equations. And over the years, I mean, my expertise is in parallel in time, which I'll explain it. I'll try to just give a brief idea of what it is in the next slide, but it's parallel in time. So you chop up the time domain into pieces. I'm coming to that. So that's my original area of expertise, but over time I have expanded into other areas which also come under algorithm development, but that's machine learning. And the third is a bit of novel storage systems, which now combines with hardware development on big supercomputers. In addition to all of that, I also mentor PhDs and various other student projects, and I've had some fantastic, absolutely fantastic students. I mean, both masters and even like placement students and some PhDs who are doing absolutely excellent work. And I've learned a lot from them, which is the best part of this. And my work, because of the variety, it involves a lot of collaborations with scientists all around the world from different fields. So it's not just fusion physicists or engineers. Many of them are mathematicians or computer scientists, chemists, etc. I'm also the inclusion ambassador for our department, which is the Advanced Computing Group, which means I promote diversity and inclusion. And I also do some outreach work, again, not as much as I would like to, but yeah, I do jet tours, which used to be real again, but virtual now. Next slide, please. Sam, next slide. Sam, you're frozen. Sam, next slide, please. Thank you. So just a very brief idea of where...
I have...
Sorry, Sam, that's okay. Do you hear me?
There's a delay, sorry.
No problem. So, right, so this is just a cross-section of the tokamak, and just splitting it up into you can divide the whole regime. This is looking at the plasma when you take a slide. And so the plasma is nothing but very hot gas, ionized gas. And you can split it up into different parts. So the core is the very central part. And as you go towards the edge, the physics becomes very, very intricate. I mean, not that the core is easy. I mean, it's difficult by all means. But when you come to the edge, now you have interactions with the wall, which means you have impurities going in, which you don't want. And sometimes you do want, and you need to decide how much you want. So it's a confusing problem, and which makes it very, very interesting. And then you have, as Walita was describing, the diverter, which is where the heat is exhausted or removed from the plasma, because that's where most of the heat becomes concentrated. And that's a research area by itself. I mean, each area within the plasma is a research topic, just to give you an idea. And some of the example problems people deal with, and there are entire research groups dealing with each individual topic I mentioned here. So one's turbulence, one is impurity transport, you have various instabilities in the plasma exhaust, which is the diverter region, and you have energetic particle transport, and this is just the tip of the iceberg, just naming a few. Next slide, please, Sam. Right, so I mentioned parallel in time. This is just to give you an idea. So this is a cartoon, by the way. So if you have a variable that varies with time, so let's say the variable is energy in this case, the energy varies with time. So the time is plotted along the x-axis, okay? Now, normally this would take forever. Let's say some of the simulations, to give you an idea, take a year to complete. I mean, simplify it a few months, and then you realize you've made a mistake, you go over, and at the end of the year, you have some simple result, maybe. So here is a new approach to it. What if, but you have supercomputers now, which have lots of processors. So what you do is split up the time series, meaning 0 to T1, T1 to T2. So you have the time domain split into various pieces, and you solve each piece in parallel. So P0, P1, P2, P3 are different processes which solve the different sections as are marked on the x-axis or the time axis. How you do that? That's the catch, because normally how would P3 know the initial condition unless P2 is done, because you're doing all of this simultaneously. I hope that I get that through the message, that you're doing all of this in parallel, that means simultaneously. And that's where the trick comes in. It's not really magic, but you have some initial predictions and you could do corrections, etc. And this is not a talk on that. So, but that's an interesting topic, as you can see. And that's one of my areas that I indulge in. Next slide, please, Sam. So just a brief. Right, so when you do such things like parallel in time, for example, is a classic case of storage. We are talking about not even terabytes, it's exabytes that we are talking about, thousands of terabytes to exabytes that we have to deal with of data. And there literally is no storage system at present that can deal with it. So there is ongoing research, and I'm part of one such project called SAGE2 with various other partners, including university and industry, which meaning Seagate in particular, who are looking into novel storage systems. And so that's, I mean, you have to find a solution. I mean, you generate all this data. Where do you put them? Next, you can't expect scientists to be looking through a huge, like an exabyte of data to do a particular analysis. So you have to have clever methods of digging in through that data and be able to pull it out. Like, I want to study what the density is. Well, you need to be able to dig out all the values of density from that huge chunk of data. So just to give an example. So that's another area I'm working on. And last slide, please, Sam, for me. The next slide is coming to data. We have lots of data from experiments, from our simulations. So we have lots of data. Could we use them? So that's where the current hot topic is our AI and machine learning, so artificial intelligence, they come in. So you have all these data. I mean, JET has oodles and oodles of data that haven't been analyzed. In the past, I mean, it was basically, it's not that we are not efficient, but it's just that lack of capabilities. I mean, we do not know how to look through that. Basically, what I was talking about in the previous slide, it's just the humongous amount. And could we use machine learning to achieve that? Because future machines like ITER are going to produce, like in one day, ITER is going to produce data that's equivalent to what JET has produced in 30 years, believe it or not. So to you be able to use that data, we could, you can use some novel methods such as AI, and that's another area I'm also looking into. So this is a very brief summary of the various interesting things I'm working on, and I hope that interests the audience here. Thank you.
Hello. So yeah, I'm Katie. I'm a graduate development engineer at UKAEA. I've been here about a year and a half now, and I'm on the graduate scheme, which is a 2-year placement scheme at UKAEA. I did a master's in physics at the University of Southampton, where I actually kind of focus a lot more on experimental stuff because I refuse to do anything software or coding based. And yeah, kind of my master's was in photonics. So it was, yeah, experimental based again. Which is a little bit different from my work now. As a graduate development engineer, I've got a kind of broad approach to what work I'm doing. So some of it's looking at control systems, which photonics does feed into in a way. But the other half of my work is as a shielding expert for STEP, doing a neutronic analysis for shielding materials. So fusion produces a lot of very fast neutrons, which need to be stopped in places because they'll cause damage to components. So you need to put stuff essentially in the way to slow down or absorb those neutrons. And you can model this using a software called MCMP, which is a radiation transport software. So you basically track where these neutrons are going, and you can work out how much stuff you're going to need to put in place, which, yeah, is kind of quite computing heavy, which was a bit of a twist in, yeah, how my work ended up being. Next slide, please. So the graduate scheme, plan one, as I mentioned, is you end up with 80% of your time as project work, so working on your technical areas, and then 20% of your time is for graduate time. And this is for personal and professional development. So this can involve training, both sort of like general training, so just sort of the skills that you'd need to help you professionally and to work in industry, as well as sort of more tailored training towards your actual role specific things. There's a mentorship scheme as well, which can help with professional accreditation and help you, whether you want to be chartered physicist or chartered engineer, you can choose. But yeah, you'll have the support and help to work towards that, as well as the training feeding into that partially as well. My experience sort of outside of my technical roles has involved some outreach. Part of that was sort of, working at sort of science fairs, tours. I also partook in FameLab, which is a sort of a comms competition or science communication. We got 3 minutes to explain a science topic. And I'm actually one of this year's sort of UK finalists. I did the KIT Fusion Summer School, which is sort of a summer school of a week of basically intense fusion learning of everything broad. So as a graduate, I didn't know much about fusion, so this was a very good way of kind of getting that very good overview of some of the best people working in the field. And yeah, thank you very much.
Okay, yeah. Frozen there. Okay, hi everyone. Yes, so my name's Michelle, and I'm also an engineering analyst. Go to next slide, Sam. So I'll just give a bit of an introduction to myself. So I've only been at UKAEA for a few months. My background is in, well, I did a physics degree, quite focused on astrophysics. So I've got a picture of a black hole. I did work on ultraluminous X-ray sources for my master's project. And then since then, I've mainly been working in aerospace. But I've actually now spent around 6 years working in engineering analysis. I kind of first got into working in analysis from an internship I did when I was at university. So I did a summer placement at Procter & Gamble, where I first kind of started using, well, it's actually CFD tools and some different kind of simulation tools, looking at modelling what's happening in their manufacturing plants. And this kind of led me to want to do these kind of roles. So yeah, then I went and worked in aerospace. I was working on gas turbines, and before I left, working on kind of quite big whole engine models of gas turbines and how they reacted to extreme events such as blade off, so like fan blade failure or bird strike. And now, yeah, I've just started working again in engineering analysis at UKAEA. Yeah, so the reason that I've kept in this field is because I think the kind of analysis we're working on is really powerful in solving some very complex problems which you can't look at analytically. There's a lot of movement in engineering towards more virtual qualification and using more simulation to kind of learn more about the systems that we're modelling and maybe not rely on so much physical testing and prototyping before we can get to a more optimum design. I joined UKAEA because it's a really good organisation doing world-class research. It's a very exciting time for fusion with a lot of investment coming in, and especially in engineering, really working towards now looking at commercially viable fusion, which creates a lot more push towards the engineering side of a fusion plant. And yeah, it means there's lots of capability developments, which are all really, really interesting. Next slide. So what I'm actually working on is the Chimera test facility. So this is a component test facility. So it's looking at, well, testings up to around a metre scale, which is being built and commissioned next year. And so it's a combined heating and magnetic loading machine. So it's basically a fusion reactor, well, fusion reactor conditions, but without the nuclear side, which kind of makes it cheaper and a lot easier to kind of run experiments. And what I'm doing on this is developing better simulations, basically, and looking at how we can move towards that virtual testing and qualification. So next slide. So I'm just getting started, so I'll just give you an overview of some of the aims that we're working on. Is really higher fidelity simulation, so we've got better predictions of how the components that we're testing are going to behave, and then being able to use those simulations then to kind of optimize the testing that will be carried out and get the most value out of testing, because this is physical testing is always very expensive and you want to kind of be getting the best information that you can. And then the kind of future aim is looking about how we can actually be using simulations to kind of augment monitoring of more complex systems, such as actually the tokamak. And then, yeah, just a bit about my role so far. So yeah, I've just been here for a few months, so I'm doing a lot of learning and lots of opportunities for me to develop new skills. I've been developing and testing new software, and also carrying out independent research to kind of get up to speed with the new area that I'm working with, and now kind of looking towards future plans and setting up collaborations with university research partners. Yeah, so that's me. Thanks for listening. I hope you found this interesting.
Thanks, Michelle. So I'm Sam, I'm an engineering analyst. I joined UKAEA in 2018. I'm in the product engineering design group. My degree is from Imperial, I did mechanical engineering, and I've got 10 years experience in analysis in the defense, nuclear, and conventional power industries. A lot of my work has been looking at arc instant modeling, a large fusion reactor. And in an accident scenario, this energy can be released in electric arcs, which can potentially cause catastrophic damage. So I've developed a modeling approach to try and predict this damage, and then if necessary, mitigating measures can be implemented. I've also been looking at some known arcing incidents, which has served as useful benchmark cases to validate my modeling approach. These images here are from that show the behavior of an electric arc in the presence of an increasing magnetic field, and you can see the kind of deflections, and this is one of the things that I have to take into account in my modeling. There's a very famous particle accelerator called the Large Hadron Collider, and when it was first ramped up to full current in 2008, it's actually experienced an arcing incident. Where it happened, you see this bus bar here connects the two large magnets in the ring, and it essentially hadn't been soldered properly. There was a gap in the solder, and when they were ramping up the current for the first time, a small gap melted and an arc formed and propagated and caused a lot of damage, including a large helium leak into the gap between the magnets, and that the pressure increase forced the magnets apart. It created a kind of domino jackknife effect, set off more arcing, and in total about 40 or 50 magnets had to be repaired or replaced. It set the program back about 8 months at a cost of $29 million. So thankfully no one was hurt, but it was a very expensive accident, and it all started from an electric arc. Around 50 to 100 centimeters of the bus bar was melted in the initial arc, and there was some collateral damage too. Here is one of my simulations for the incident. Hopefully it will play. So yeah, you can see it happened very quickly over a second, but that second's worth of incident proved to be very damaging and expensive. Here is a kind of photo from the incident. It's symmetrical, so if you imagine splitting it by the horizontal plane and comparing it with the simulation, you can see a similar kind of pattern in the damage. Good match there. So we have a method that we've been able to approach now to predict potential accidents in fusion power plants. Okay, I'm now going to move on to talk more generally about life at UKAEA. As I said before, we have two sites. One is in Oxfordshire, in Culham, the Culham Science Centre, and very recently we have the Advanced Manufacturing Centre in Rotherham in South Yorkshire. And there's been a lot of investment in new buildings and hybrid working infrastructure too. Over the pandemic, it's been recognised that a lot of people do work effectively from home, at least for part of their week. And so what we've invested heavily in is these suites where people who are on site can work effectively with those who are working from home. We have excellent on-site catering facilities, including a subsidised Costa, which is fantastic. We have an excellent pension schemes, which are essentially extra bank holidays, committed to equality, diversity and inclusion. This is taken from the employee handbook. It says, the UKAEA is committed to valuing diversity and seeks to provide all staff with the opportunity for employment, career and personal development on the basis of ability, qualifications and suitability for the works, as well as their potential to develop into the job. This is our vision, launched last year. It says, being inclusive encapsulates our vision to be an employer of choice that attracts, retains and develops people to their full capability, because our reputation for valuing and celebrating all forms of diversity is widely acknowledged. And here are some of the things we do. So we're a bronze award holder with the Athena Swan. We have 20 mental health first aiders. We have 35 inclusion ambassadors. We sponsor external EDI related events. We're in the process of formalizing 3 internal employee networks, membership of advanced higher education, which is Athena Swan, inclusive companies, Versida, Employers Network for Equality and Inclusion, and Black British Professionals in STEM. We have a parent network, we have maternity buddies and frequent EDI blogs. This is Marcia Orr, and she is our Equality, Diversity and Inclusion partner, and this is what she says. Legislation and policies provide legal protection and guidance. However, it is our individual and collective daily actions, our attitudes and behaviours, conscious and unconscious, where the impact of equality is taken very seriously at every level of our organisation. Publicly funded projects, for example, Mast Upgrade, which is our project in the UK, JT60SA has recently come online in Japan, and the largest project of all is ITER, being built in the south of France, and this is being assembled as we speak. And the UKAEA is playing a crucial role in supporting these large international projects. But there's also private investment too that is increasing all the time. These 3 firms here, these companies at the bottom, are just UK fusion startups, and there are plenty more internationally. So taken together, when you have when you look at the public and private, very much maturing as an industry, and it's no exaggeration to say that now is the most exciting time there has ever been to get involved in fusion. And just to summarize then, we hope we've made it clear that engineering analysts and HPC specialists are our key, distinct, defined roles at UKAEA. As a company, we're supporting all areas of fusion, research and development internationally. And STEP, our own project, will be the UK's first fusion power plant. As a company, we have a firm and demonstrable commitment to EDI at every level in the organisation. And all in all, it is a very unique place to work. And we would like to encourage anyone who would like to find out more to visit these 2 websites or get in contact with us via email directly. You can follow us on all these social media platforms, and we would be very grateful if you could fill in this brief survey. You can take a picture of this QR code on your phone. I'll also paste the link into the chat. It doesn't take long, but especially if you'd like to get in touch with us, please do fill in that survey. I'll now hand back to Abby and Karen, but from all of us, thank you very much for joining. We hope you learned something and found it interesting. So thank you.
Thank you, Sam, and everybody. That was a brilliant talk. Really, really good. I have a couple of questions, if that's all right. So some of the PhD students I speak to are torn between what to do when they leave, what to do when they finish their PhDs, whether to continue with their academic career or to go into industry. What would be your advice to them?
Okay, I'll just take the lead here. It depends. I mean, for people like that, we have something called, I mean, it doesn't have to be a PhD though, because it also caters to students with masters, is the graduate scheme. But we have had people who have done PhDs, and the graduate scheme, we have members here, like we had speakers today. Katie here, for example, is part of that. Is the whole idea is you work in different departments. So depending on your interest, and you try to get a flavor of each. And so you work with different people. So that is also another learning experience, because you will work in groups and not each group are the same. And you will be able to discover what you like best. And we have had, I mean, I think our CEO came through that. Before that, our chief operating officer came from that. So we have had lots of people from the management who were once graduates. So it's a very, I mean, if that's not a selling point, I don't know what is. So yeah, that's something we have at UKAEA.
And how many graduate places do you think annually available?
Good question. I think it varies. I don't want to give a number because I could be wrong, and I don't want to mislead. Anybody can help me with that?
Yeah, so I think my intake, which was 2 years ago, there was 30 taken in. The latest intake, so this current year, it was 40. So I think they're increasing every year as to how many.
I think it varies depending on the funding. And since we have funding going up at the moment and with more departments, that's definitely the case. You can apply to, it's an online application. So if you go on to the Jobs UKAEA website, you should be able to find how to go about it. And also, if you're interested, if you don't know exactly, I would strongly recommend anybody should throw in their CVs in the talent pool. So there are, like, if you're you don't know what you want to do, but you are a computing person, so just throw in your CV at the advanced computing group talent pool, and yeah, they are looked at and sorted very regularly. So there might be an opening and you might be invited.
That's great advice. Thanks.
I just wanted to thank you all for such a wonderful talk, and it's so nice to see industry and research combined in such a wonderful, wonderful way, and all your EDI initiatives and whatnot. It looks like a wonderful place to work. I'll just say, as a child, I grew up in Abingdon, just outside of Abingdon. So I spent all my school trips coming to see you guys, and also Harwell down the road. And I would like to credit that this is probably why I'm doing a PhD now, maybe, possibly, who knows. So I just also wanted to compliment the explanation of parallel computing. With my theory, we do a lot of parallel computing, and I've never seen such a concise and wonderful explanation. And I would love to steal that for when I do my own talks about parallel computing. So thank you so much for that. I have a question before I go to some of the questions in the chat. Oh no, they were just adverts. Okay. What do you think the main differences are between the research you do in a PhD and the research you do there on the campus? So
I think you're going to have to answer that again, Debbie, because I don't think the rest of us have PhDs.
All masters. So what's like the difference between university research and this research there? What's the main differences? What's the positives, negatives?
It can be a mixed bag, in the sense that it depends actually the kind of work you do, because we have some people who carry on pretty much with what they were doing at university. I mean, that's an overstatement, but it's I don't want to sound wrong. It's about, it was the same area of research you were doing, and you do the more application based here, if that's what it means. But I have to highlight, we work a lot with the universities itself. Like, for example, me, I mentor a lot of PhDs. So there is a finite amount of research going on, or at least I have to be on track with researchers being developed at universities. But obviously we are an experimental facility, and our main focus is to put electricity on the grid. So yes, I mean, of course, it's applications that we are looking for, but those applications wouldn't happen, because again, this is an experiment we are doing. This is not a real industry yet, fusion. So there are lots of unanswered questions, and we regularly interact with people who are trying to answer those questions. And some of us ourselves are also trying to answer those questions. So it depends a little bit on the specific group and your specific area. But UK is a perfect blend, I would say, of absolute theoretical research and an industry, because it's neither of both, actually, in reality.
Yeah, I do think it is. I mean, I've been here for a few months, but I think it is a very good balance. So obviously, yeah, did my master's project, and I guess moving into industry, it's a bit more applied, or it can be a lot more applied with the research you're doing. So going from aerospace, where we were still working with universities a lot, but we were a lot more focused on kind of like the benefits of the research that you were doing. Like, it had to be very kind of strictly planned and very strictly related to something that would then go on to, well, be for like a commercial endeavour. Whereas at UKAEA, we're kind of taking a step back a little bit more, because we are still having to do more research, which is more wider scoping than very focused research that you're maybe doing in some more commercial industries, such as automotive or aerospace. So yeah, I guess it depends where you end up, really, about whether you're more research focused or more kind of very industrially focused with what you're doing.
Yeah, just to echo that, in engineering as well, you can get involved in supporting the sort of current experiments, and that might be more shorter term kind of deliverable based work as opposed to longer term research. And one thing that is actually really great about UKAEA is the management are really good at trying to tailor the work they give you towards what you kind of would like to get into where they can. So if you were wanting to sort of get into the kind of higher pressure kind of operations or support, then you can do that. Alternatively, there are a lot of work, as everyone mentioned, in the sort of more longer term research projects.
It sounds like a really wonderful mix, and you can get to taste everything, you know, and I think that's absolutely wonderful. So this is purely for my own benefit and the outreach and EDI that I do, but would you say that the skills that you learned from your STEM degrees, and obviously you guys have done such variety of projects in your careers, and you've ended up here, is just amazing. What do you think the best skills I can feed back to an undergraduate cohort are, the top skills that you got from your undergraduate masters and whatever experience that has made you such successful individuals today? I know that's quite weird, but it's something I've been asking everyone recently. So
I guess my physics degree, and I've done quite a few different things since then. I mean, it gives you a very strong foundation in kind of the fundamentals of, I guess different physics degrees focus on different things, but in terms of like electromagnetism, quantum physics, I also did programming in my degree, which was also really helpful. And then also I think just the skills of scientific writing, which you just continually use. And we didn't probably do it an awful lot, but even just starting to build up presentation and communication skills is obviously vital. You keep using it throughout your career.
I may just add that we have had people, lots of them actually, now doing operations, who or even in advanced computing group, who were first particle physicists. So that just tells you that how particle physics has nothing literally to do with the tokamak, and it's the problem solving skills. It's what you learn. So it's more the method than, a particular topic. Because these people are really great. We have some of the best people from particle physics. I wouldn't say that particle physics is bad and fusion is just awesome, which is true, but let's not say it.
One thing that I think, may I add something?
Go for it.
Yeah, for example, in my life, I didn't imagine to become like I am engineering, system engineer. And then I did a master's in computer science. Then I did a master in HPC, high performance computing. Now I'm see something about nuclear engineering. And I know that I have some lacks, many lacks about, I mean, anyone knows anything or everything. Sorry. So I have received some help from some specialists, and I'm learning in the way. And there are some, for example, there's going to be a school, summer school in plasma. And I'm very excited about that. I know that I have to reshape my skills in math and again in physics. And sometimes we might say, why this lady is so excited about learning math and physics and computer? It's so geek. But at the end, the result, I mean, it's phenomenal. It's related, and you can feel like the satisfaction. At least if you are very aware how the particle moves or the neutrons and why does the direction, there are thousands of variables on it. I hope I can make it. I mean, all these things to be able to share all my knowledge with the new generations, ladies specifically.
Good.
So the only thing you need is the willing to do it. I think if you are very interested to be part of this.
No, that's so true. It is the will, like everything, you know, because you can put your mind to anything. I did 2D conformal field theory as my master's, and trust me, you need a lot of will to do quantum field theory. But you know, that's amazing advice. I think from you guys have got you know the problem solving skills and you know the scientific writing and coding and all the things you learn the way, but also that kind of will and determination, and also to keep on learning, because learning is so important. I think the one last question is, what is your favorite thing for working at where you work and in your departments? What's your most favorite thing that gets you out of bed in the morning or afternoon, depending on your working hours? So whichever of you want to go first.
Just quickly, I think in my case, particularly, my brain somehow grows. I mean, I'm faster. I'm aware. I can do many things at the same time. I did that in the university. I did that in my previous jobs. But now, because my head is related in this goal, like the tokamak thing, learn about each component, somehow I feel like more lucid. I like that. And I improve my concentration as well, the skill. I can say that. Mm-hmm. And thank you so much for the invitation, Abby.
Oh no, that's amazing. I like that. Improve concentration. That's pretty interesting. That's really good. So what about, feel free.
Okay,
favorite thing about work?
It's I think for me, I would say it's absolutely not boring, because because it pushes you out of your comfort zone. I mean, there are things I do now which I didn't even know about a year ago. And that has been throughout my career. And I think that's what, for most of us, I think I'm speaking for everybody here, it pushes you out of your comfort zone. There is support available. But having said that, I think I would be comfortable the first day if I was doing the same thing, but within a week I would be bored. And I think Walita was actually touching on that point, that it keeps us going. It's exciting. And for me, there's another important thing is, and I think it's the same for others as well, is fusion is after a game-changing thing. It's, if it works, it's going to change the world. So just to have that feeling, I mean, with our skills, we could be in any other industry, to be honest. We are not there, we are here with all the pros as well as the cons. I mean, it's not a perfect world, what we do. I mean, I think we would all be paid higher in some of the other industries if we went to, honestly, but we didn't. And I think it's the philanthropic aspect of it. I think that keeps us going as well.
That's great. Thank you, everybody. I'm conscious of the time. We've overrun slightly, but it's been absolutely worth it. Your talks have all been so fantastic, really succinct and interesting. and hope that our small but very special number of attendees are enthused to look further into working for UKAEA. And I look forward to us working together in future. So thanks, everybody.
Thank you very much,
Thank
Karen and Abby.
you.
Thank you.